In this lecture, we are going to talk about what are the implications of scaling on the performance, why do we scale, what is the story behind the success of MEMS. There are lots of companies out there nowadays that are making 1 billion MEMS per year or more. What is the reason behind this kind of level of success? And then we also quickly look at the markets for different MEMS devices let's say maybe an introduction to why MEMS devices are so popular and why it has become such a huge field. And then you will see over this lecture that why is it such an enabling technology for other areas like IoT or wearables or things like that. So let's look at the scales first. Here is a axis logarithmic scale going from about 1 angstrom, 10 to the minus 10 meters, to about a meter, right? And then there are some familiar objects here. So about the hydrogen atom is about 1 angstrom in diameter. And you have seen a lot of these microelectronic chips. They're usually about a few millimeters on the side. So the package and the pins and all that, they are about a few millimeters, maybe a few centimeters for a big one. And then an E. coli bacteria is about a micron, right? A micrometer is 10 to the minus 6 meter, or 1,000th of a millimeter. Now, the coronavirus, the familiar foe over the past year or so, is about 100 nanometers in diameter. The MEMS device, the microelectronic systems, the transistors and then circuits based on transistors that you learned about in your 251 course, the integrated circuits. The dimensions, typical dimensions, are about 10 nanometers for your transistors all the way to maybe a few micrometers per transistor. The chips are actually bigger than that. Nowadays, you're talking about transistor dimensions, the gate lengths that are on the order of few nanometers, 4 to 5 nanometers. But for most devices that you can design and use, the dimensions are on the order of 10 nanometers to maybe a micron or two for the transistors. The chips are about a few millimeters on the side. Nanomaterials cover the range of about a few nanometers on their smallest sizes or smallest dimensions, all the way to maybe a few tens of microns for the longer ones, right? So for example, a nanofiber can only be 5 nanometers in diameter or 2 nanometers in diameter, but be several tens of microns long, or even maybe longer than that, millimeters long, right? So nanomaterials cover that portion of the spectrum. MEMS devices are typically in the range that are shown. The critical dimensions are on the order of micrometers or so, a couple of micrometers to maybe half a micrometer. So what do I mean by critical dimension? It means the minimum beam width, or the minimum distance you can have between two structures, or the minimum thicknesses of the layers that you can use. Those critical dimensions are on the order of microns, let's say within a factor of 10, and they usually don't get much larger than a couple of millimeters on a side. So most MEMS devices, the device itself, the largest dimension is on the order of tens to hundreds of microns. Sometimes it goes up to maybe a millimeter or two, and very, very rarely exceeds that. So that's the scales that we are dealing with. For MEMS devices that are integrated with circuits, you obviously have a wider range. And then if you include the package in your, let's say, dimensions, or in this table, you're talking about a few millimeters for most of these devices to a few centimeters from outside, from where we can use them. Examples of microsystems, well, there's plenty of them in nature. All the cells, the capillary blood vessels, small insects, these are all microsystems. They have organs and components that are on the order of, few microns or even smaller, that collectively work together and make the system function as it is supposed to. Among man-made devices, there is plenty of examples of microsystems from the past, right? So if you look at watches, a lot of them have components. I mean wristwatches or watches that were made, let's say, 100 or 200 years ago, have components that are finer than 1 millimeter. The resolutions are finer than 1 millimeter. The accuracy or precision in fabricating them is actually much beyond that. Microdrills have blades that are that small, various metal coatings. We have been coating metal for centuries now. And these coatings are usually only a few microns thick, right? So you can look at all of these as examples of micro devices, micro layers, micro systems that were fabricated in the past. However, the fabrication technologies that we were using in those cases was serial. Right? You made one device at a time, like an automotive manufacturing facility. You make one car at a time. Or a lot of other fabrication facilities that you can think about. It's a serial manufacturing process. You make this piece, then you go to the next one, then you go to the next one. For that reason, these systems are expensive because it's a microsystem. It takes precision and care to make it. And if it is one at a time, you spend a lot of time making one device. Nowadays, we are doing it in a different way. So the typical, I would say the most common microsystem that is around you is a microelectronic circuit. And there are micromechanical devices, sensors, and optical components and fluidic components around you. We are not making them one at a time anymore, right? So for these kinds of devices, because you want them everywhere and you need them in a lot of applications, we have found ways to make them in parallel, hundreds of them, thousands of them, or tens of thousands of them at once through these microfabrication technologies. And that's the topic of the course for the first 2 or 3 weeks. We want to see how these are made. Obviously, it's a new manufacturing technique, different from what you do to make a car or even a cell phone. We make these devices in parallel, but and then we'll see that the processes are fairly complicated, and the facility that you need to make these devices is fairly complex and expensive to put together. But because we're making 1,000 of these devices at once, or 10,000 of them at once, the cost is distributed among those many units. So if a silicon wafer costs me $5,000 to finish, from the beginning to finish, but it has 10,000 devices on it, the cost per device at the end of the story is 50 cents. And this batch fabrication has made 2 things possible. Firstly, I will have a lot of these devices. I can make hundreds, thousands, millions of them. And secondly, the cost is low. The cost per device is low. So it's systems that will need these components now. You can design systems that utilize these components, and then they are not going to break the bank. Applications and trends right now, you will see that a lot of hype is around IoT and IoT-based technologies, including smart automotive. You can think about it as an IoT example, right? But you'll be talking about smart cars nowadays, that the cars that are able to drive themselves and they can communicate with the infrastructure, other cars, and detect passengers and hazards on the roads. You need sensors to figure out what is going on around you, and you need electronics to talk to other smart systems around you. Mobile devices, laptops, tablets, cell phones, all those, wearables, all of those are huge. 5G is opening up new opportunities for making these low power distributed networks of smart sensors. We have data centers that are processing everything about us, right? So whether we like it or not, they're collecting this data from usually different sources, but in case of people, it could be their browsing history all the way to where they were, based on GPS data or even, environmental information. And they need storage devices, they need memory devices, they need electronic circuits. AR, VR, voice processing, all of these are different segments of the market that are going to need microelectronic and microsystems, and it's just expanding. There's no stopping, right? So all of these areas are getting bigger and bigger by essentially the day. Some of it is not really there yet. Healthcare, there is a huge potential for an explosion in applications in healthcare areas. It's still not there, compared to, for example, when you look at it, smart automotive, it's about 10% of that, but I'm almost certain that it will surpass automotive market in the coming years. So MEMS market, as of now, is dominated by sensors. You can see that they have been a major portion of this microsensor sensor and MEMS market since at least 2015 in this graph, but since the beginning really. And it's going to stay like that, right? So the sensors that we're using in IoT and all the other applications, we're going to need more and more of them. The wireless earphones that you were using, a few years ago, you had a speaker in them. That was it, right? Now, the wireless earphones that you're using right now, they have, in some cases, multiple microphones to detect the sound around you and use it for noise cancellation or basically filtering it as needed in some cases. And they're talking about using MEMS speakers in them as well, so that you can make them smaller and basically improve the sound quality at the same time. So all of these are adding to the demand for MEMS devices. A good portion of the MEMS market, the one that grew quite a bit over the past few years, is RF MEMS, where you need filters for basically separating frequency bands for telecommunication applications. And they figured out how to do it with MEMS technology. So you're basically using mechanical filters at gigahertz frequencies. And because of the explosion in the mobile market, you need more and more of such filters. And there is such a tight restriction on bandwidth usage that you basically have to optimize the amount of frequency band that is available to you, so that basically you pass more information, more data, more customers. And for that reason, we are seeing more and more RF MEMS components deployed. These are actually more than 10 per mobile device nowadays. And there are other sensors, right? So if you want to look at it as a chart, as a pie chart, again, it's a lot of it is sensors. On the right side of this pie chart, you see mostly sensors. On the left side, the microfluidic part is the part that is growing, and it probably will keep growing. And the microfluidic part is important because it relates with the healthcare, right? So in healthcare, you have drugs, you have biosamples. A lot of those interactions, chemical or biological, are happening in a liquid environment, and you have these microfluidic systems for processing those kinds of information and data. If you look at the markets, who is using MEMS, again, the segmentation is shown here. Growingly, it is consumers. We're coming up with more and more use cases for consumers that rely on MEMS. IoTs and wearable are the latest ones, but industry is also using more MEMS, right? So Industry 4.0 is about doing things at the right time. And how do you do the thing at the right time? Well, you have to monitor the environment. You have to know when you're running out of such and such supply and replenish it if you need to. And therefore, you need sensors everywhere again, right? And automotive is going to, again, because we want to make the car smart and aware of the environment, is going to grow in terms of their reliance on sensors. A lot of these items here are familiar. Now, another thing that is happening in the MEMS domain is that we're using MEMS sensors individually. So maybe you had an accelerometer that you used for activity detection, and then sometimes maybe you joined that accelerometer with a gyroscope and try to do some navigation with it and things like that. But in most cases, we were using individual sensors. Now we're using sensor hubs, right? So for example, in terms of navigation, now there are modules that you can buy or chips that you can buy that have an accelerometer, a gyroscope, and a magnetometer on them. And therefore, you can use them to do the navigation, inertial navigation. You have environmental sensors or sensor hubs nowadays that have gas sensors and particle sensors integrated onto the chip. You have to know the pressure, the temperature, and maybe even sound, right? And then you have also optical sensor hubs. So there's a trend to integrate more functionality into these chips and microsystems by adding sensors of different kinds, right? Not the same type, but maybe gas and pressure and humidity. These are different types of sensors. Who is making MEMS? Well, Bosch, basically the suspects are those who are good at microelectronic fabrication. MEMS, microelectromechanical systems, is utilizing a lot of the expertise and knowledge and know-how and systems that were developed for microelectronic processing. So it is, I think, expected that those companies will remain major players in the MEMS field as well. That was true for a long time, but recently there are companies that are focusing on some aspects, right? So they may not have a history in microelectronic fabrication. So for example, Broadcom here, that is a manufacturer of RF MEMS, they were not known for making their own chips before, but now they make their own MEMS. And they're very successful because they're making all those MEMS filters. And as you can see in the chart here, all of a sudden it has pushed them up to the first place in manufacturing, in terms of manufacturing of MEMS devices. They're making the most out of everybody else. You know, all those that make sensors and all that, they're making less MEMS than Broadcom, which is only making RF MEMS. But you know, companies like ST Microelectronics, Robert Bosch, HP, they're basically well-known names in microelectronic industry. In terms of business models, there are three different approaches. You look at the cost to make your device and what you need to make your device. If you look at the microelectronic industry, a vast majority of the companies don't make their own chips anymore, right? So they're basically relying on external providers, service providers to fabricate their chips for them. So there's a few of them left in the world because the microelectronic fabrication is really expensive and it requires a lot of investment at the beginning. It requires you to run the fabs at 90-something% capacity to make any money, and your fabs become outdated in a few years. So you have to make all that investment, you have to get all that money back within a few years and by running the fabs at near full capacity. So in microelectronics, what has happened is that it's a consolidation of service providers. There's only a few of them, like Samsung, like TSMC, like maybe even Intel, you can count it as one. Sony, there's a few of them left in the world that can actually make microelectronic devices for you. And the other companies design their own chips and ask these folks to make it for them. The good news what happens over there is that, you know, the circuits are very different, but they're all using the same fundamental component, which is in most cases a metal oxide semiconductor transistor. It's a MOSFET, right? So the schematics could be very different, but the fundamental component is the same for all of them. In MEMS, that's not the case. In MEMS, you know, if you're making an accelerometer, your process flow is going to be very different from the ones that are making a pressure sensor, and those that are making a gas sensor, and those that are making a gyroscope even, right? So for that reason, it's not that easy that if you have an idea to make a device, to find a foundry that can do it for you. They may be able to do it for you, but you have to have the right volume and the right number of customers in order to convince them to make it for you. And sometimes you may have some very specific processing step that an external foundry doesn't have it, right? So, and they're not really interested in developing it for you. And in that case, you have to still make your own device. So there are three types of models that MEMS companies follow. One is fab, right? So fab means that you fabricate your own device. You design it and you have the facility to fabricate it. But you have to be a big and rich company to do that. Fabrication is expensive, and as I said, you need to make sure that you can recover the money that you invested in a fab, in a facility. A good number of the remaining companies are called fab light. So what they do is that they rely on an external service provider to do most of the fabrication for them, but there's a couple of specialized processes or process steps that they have to do in-house for different reasons. Sometimes it is because the external provider doesn't want to do it or cannot do it, and sometimes it is because you want to keep it a secret to yourself. You don't want to give it, let anybody else use it for you besides you, right? So a lot of the MEMS, there is a good number of MEMS companies that are called fab light. So they do the fabrication, but usually only towards the end of the process line, and only a couple of steps that are usually not available through external service providers. And then there are fabless companies, and these are companies that are approaching the MEMS design as the microelectronic companies, you basically give out the entire fabrication to a service provider and you may ask them to make it for you. What has happened over the years is that companies that were good at microelectronic manufacturing, like TSMC for example, have developed the capabilities to make MEMS. And they have certain processes in place, certain steps in place that they can provide to you and tell you this is what we can do, design within these limits. So if you can come up with a fabrication process flow that uses those steps and doesn't need anything new, and you can just put them in the right sequence, they can make the device for you. It has some limitations. Well, you have to basically follow whatever the steps they give you. You usually do not have the freedom to change them at all or that much, depending on how big you are and who is the person on the other side of the table. But it's an approach that a lot of companies are taking because it just gets rid of the fabrication process for them, or worrying about the fabrication process for them. And consequently, they can just focus on design. There's probably a trade-off in terms of performance, but the savings on the cost is probably justifying it. Most of the MEMS startups are usually fab light. There is usually a trick that you have in order to start a company. And the big ones are either fab or full fab or fabless. So now what happens when you scale down the device dimensions? So the video that you saw in the previous slide, or like video, lecture video, showed you an example of an accelerometer, right? So we said there is a big scale, large scale accelerometer that you could use, but engineers in the 90s came up with these micro accelerometers. So you went from, let's say, 100-gram proof mass to something that is on the order of a milligram or less. What is the effect of this on the performance? So in here, we're going to go through some of those major issues. So let's assume that we scale down the linear dimension by a factor alpha. So in this case, we're going to assume that alpha is larger than 1. So let's say I go from 1 meter to 1 millimeter. So alpha is going to be 1,000, right? So if I scale the linear dimension by factor alpha, the area goes down with a factor of alpha squared, right? So if you have a 1 meter by 1 meter square and you scale all dimensions by a factor of, let's say, 10, the area of this new device or feature is 1/100th of the original area, or that was 100 times larger than what you get at the end. Mass is proportional to volume, so mass and volume go down with a factor of alpha cubed, right? So if you, I think it is understood. Inertia, same thing, goes down by a factor of alpha cubed. Electrostatic energy goes down with a factor of alpha cubed. Now, this energy is the energy that you store between two electrodes. So if you keep the electric field constant and shrink the dimensions, what happens is that as long as the electric field is constant, it means that you have to reduce the voltage. So the electrostatic energy will be proportional to the volume between the two electrodes, and it is going down with alpha cubed. However, if you look at electrostatic force, it goes down by a factor of alpha squared. And again, you can see that things are maybe shifting in one direction or the other, because the force is going down with a factor of alpha squared, but mass is going down by a factor of alpha cubed. So what is going to happen is that if you push that alpha large to a great extent, electrostatic force that I normally ignore in large-scale applications, in macro scales, may be becoming important at small scales, right? Because at small scales, the force is not dropping as fast as your mass, so therefore, you have more opportunity to get acceleration, to get mechanical movement out of your structure. F is equal to ma. So if your force is scaling down with alpha squared and mass is going down with alpha cubed, now maybe you can get more acceleration out of it, more movement out of it. So maybe electrostatic actuation becomes more useful as you make the dimensions smaller and smaller. And we'll see that is actually the case. At small scales, electrostatic actuation is actually one of your major actuation mechanisms. Coulombic force goes with alpha to the -2. So that's great if you make, if you have 2 coulombs of charge or 1 coulomb of charge on 2 different items and you bring them closer to each other, the force goes up. But the challenge is that you cannot really get that much force, that much charge on small objects. If you could, that would be great. You get a lot of force out of it, but it's not that easy, So it looks great here. In practice, it's not that easy to implement it. Magnetic force, however, goes down with alpha to the 5. And again, this tells you, so this is a constant J, constant current. So if you have a wire, constant current density, if you have a wire with a given cross-section, you're shrinking the dimensions of the wire and you're bringing them closer to each other. So you know that if you pass a current through a wire, you produce a magnetic field. If you pass a current through another wire that is nearby, you produce a force onto this second wire because of the current and magnetic field that you have. Large scale, this is how your AC motors run, right? Basically, a vast majority of the movement you have industrially and in consumer applications is because of this magnetic interaction between wires that have current through them. So it's widespread at large scales. 60% of electricity in the world is used for motors, by motors, right? But shrink the dimensions to the scales that we are talking about, microns and so on, and the force goes down with alpha to the 5. So even though this is a major actuation mechanism at macro scales, at micro scales, it becomes almost useless because of the inefficiency that you have. The defect density, it needs a bit of explanation. So let's assume that we have a certain number of defects or particles that are going to come and sit on your surface. Well, if you reduce the dimensions of your device, the chance of having a particle where your device is reduced if the number of particles in the air is constant, right? So what this means is that if you're making these devices in parallel, if you're putting 100 of them in parallel, and let's say you have 50 particles that fall off and kill 50 of your devices, if you make your devices smaller and put 1,000 of them in parallel instead of 100 of them, and you drop the same 50 particles, 950 of them will survive your new devices. So this is another motivation to make your chips, your devices smaller. You make more of them so you make your money, but also few of them will have yield issues. You will have functionality issues. Deflection on their own weight. Well, this is to just imagine this. You have a beam, and if it is made of metal, wood, whatever, let's say it has a free end, it's going to deflect under its own weight, right? The gravity will work on this beam and just pull it down. As you shrink the dimensions of this beam, you will notice that the amount of deflection goes down with alpha squared. What that means is that the amount of deflection under own weight quickly becomes irrelevant. At these small scales, the masses of these devices are so small and the dimensions are so small that in most cases you actually can treat them as massless items, right? So the mass of this device doesn't affect its initial static location. Of course, when you talk about the dynamics, you have to take the mass into account, but for static applications, the mass of these devices is so small that you can just ignore it in most cases, not all cases. And resonant frequency, which is a measure of how fast your mechanical system responds to an input, goes down with alpha to the -1, meaning that if you make the system smaller, if you take that beam and make it 1/10 the length, its resonant frequency goes up by a factor of 10. Well, I mean all dimensions go, if you scale all dimensions by a factor of 10. So these small devices respond faster. They act more quickly on command signals. So that's another opportunity, right? Now, on the left side of this table, you will see some advantages and disadvantages of scaling. Obvious advantages: they're lighter, the devices are lighter and faster, they consume less power, and because they're smaller, you can put multiple of them in parallel with each other and have an integrated system. The disadvantage is that the forces are smaller. You cannot harness power. A lot of power that you receive from the environment, let's say solar, is proportional to area. So once your device is smaller, your area will be smaller, and then you cannot harness as much energy. Friction becomes a major issue at small size, and then cost of manufacturing is high, but cost per device can be low depending on how you do it. So there are pros and cons for scaling the device dimensions down, and we'll see that we're going to miniaturize systems when the advantages are basically the argument for the advantages is stronger than the argument for disadvantages. And we'll see, so in some cases there's no choice. You really have to do it at small scales. So challenges at micro scales or different scales. Well, at macro scales, positioning is easy. You just put whatever you want and place it wherever you want. Velocities are on the order of meters per second to centimeters per second maybe. Force sensing is easy. You just attach a sensor wherever you want to measure, a strain gauge to wherever you want to measure the strain or forces, load cells, right? And dominant forces at these large scales are gravity and friction. Throughput is usually through serial assembly. You make one device, then you go to the next, then you go to the next. And manipulation is, in most cases, mechanical. You grab onto something and move it. And you see what is going on. At micro scales, positioning is very difficult. You're moving stuff, or you want to move stuff that are on the order of 1,000th the diameter of human hair, or maybe 1,000th of a millimeter, 1 micron or so. The velocities are low. The force sensing is difficult. You really cannot attach a sensor wherever you want. You have to make it as part of the structure. It has to be taught, or you have to think about what you want to measure during the fabrication process, not even the application, but during the fabrication process. If knowing such and such parameter is important to you, you probably have to do a couple of extra fabrication steps to incorporate it into your structure. Dominant forces, friction is huge. The surfaces are so smooth that if you bring two of these materials or devices together and they touch, they usually stay stuck to each other forever. The surface forces, van der Waals and other, are so large that you really do not have enough force to move them apart from each other. The fabrication method is batch fabrication. You do not make one at a time, you make 100 at a time, or 1,000 at a time. And manipulation, if you want to move something, it has to be micromechanical. There are some optical ways of doing it, but in most cases, you basically try to just avoid it. If you can just let this stuff be where they are, manipulation is very difficult at small scales. And vision, you cannot see these things with naked eyes. So normally I had samples that I would bring to the class and pass on to the students. Unfortunately, it's not possible here, but you can do a search on the web and see the type of scales and dimensions that we're talking about here. At nanoscales, things are getting a little bit trickier. Now, one issue is that with nano devices, I'm not talking about nano electromechanical systems. I'm talking about nano devices or nanoparticles, and you can take advantage of what chemistry provides to you, right? So, for example, techniques like self-assembly can be used to arrange these nanoparticles in certain ways and then take advantage of their properties. So that's the concern of some other topics, some other courses. We're not going to talk about that here, but I have it in this table just for the sake of clarity. So let's have a video on the world of microscopic machines. Again, the link to this video is provided. And if the audio is not good or the audio quality is not good, you can actually go and check the video online.
Virtually every vehicle made within the last 20 years contains an astonishing piece of technology that remains dormant, sometimes going unnoticed for years, until the unthinkable happens. When an airbag deploys, the electronics of the airbag system take just 15 milliseconds to decide if the forces on the vehicle are severe enough. Within 60 milliseconds from the instant of impact, the airbag is fully deployed. The entire process from initial vehicle contact to deployment happens at twice the speed of a blink of an eye. And at the heart of an airbag system is the same technology that allows our smartphones to detect motion, inkjet printers to print, and projectors to throw an image on a screen. These technologies all rely on the emerging field of microelectromechanical systems. Microelectromechanical systems, or MEMS, are tiny integrated devices that combine mechanical and electrical components. Traditional manufacturing techniques such as milling, turning, and molding become impractical at small scales, so MEMS devices are fabricated using the same batch processing techniques used to fabricate integrated circuits. These devices can range in size from a few microns to several millimeters. What makes MEMS devices so powerful is their ability to sense, control, and actuate on a microscopic scale, yet generate effects at a macroscopic scale. MEMS technologies are highly interdisciplinary in nature and require engineering and manufacturing expertise from a diverse range of technical areas such as integrated circuit fabrication technology, mechanical, electrical, chemical, and fluid engineering, as well as material sciences, optics, and instrumentation. Their applications span across several industries, all of which are manufactured inexpensively and in high commercial volumes. Because MEMS devices are a hybrid of mechanical and electronic mechanisms, they're generally fabricated using a combination of traditional integrated circuit technologies and more sophisticated methods that manipulate both silicon and other substrates in a manner that exploit their mechanical properties. In traditional integrated circuit manufacturing, known as photolithography, a wafer is first coated with a substrate of silicon and its surface is oxidized. The oxide surface is then coated with an ultraviolet sensitive polymer called a photoresist. A pattern of ultraviolet light is projected onto the photoresist, which is then chemically developed into a mask on the surface. During mask development, the more common positive photoresist becomes removable by the developing agent when it's shielded from UV light, while a negative resist is removable in areas exposed to UV light. Atoms are radiated onto the exposed regions, penetrating into the silicon beneath, in a highly controlled manner, changing its conductive properties. The unmasked oxide layer is chemically etched away and the remaining photoresist chemically washed away, and this process is repeated dozens of times using the remaining layers of oxide as a mask for each subsequent layer. The buildup of layers of material with different semiconductive properties form the circuitry of the chip. Aside from its electrical properties, silicon has excellent mechanical properties as it forms the same type of crystal structure as diamond, though much weaker, and it is harder than most metals. It's also surprisingly resistant to mechanical stress, having a higher elastic limit than steel in both tension and compression. MEMS fabrication, much like integrated circuit fabrication, involves the addition or subtraction of two-dimensional layers on a substrate based on photolithography and etching. The 3D components of MEMS devices are due to patterning and interaction of the 2D layers stacked on each other. The manufacturing process for these devices fall into three general classifications: bulk micromachining, surface micromachining, and high aspect ratio micromachining, or HARM. In bulk micromachining, the substrate is removed in a manner similar to traditional integrated circuit techniques. An oxide mask is created and the exposed substrate is etched away. The pattern of etching is determined by the type of etchant. Isotropic etchants remove material equally in all directions, while anisotropic etchants are limited by the geometry of the structure to be etched. Anisotropic etchants usually etch faster in a preferred direction. The etch resistance of the substrate can also be controlled by selectively bombarding it with atoms of boron in intermediate steps, using traditional photolithographic techniques. While traditional wet chemical etchant can be used, a more common approach is the use of a reactive gas driven into a plasma state via radiofrequency energy in an etching process known as reactive ion etching. Surface micromachining, by comparison, is predominantly additive in nature and is used to create more complex MEMS-based machinery. Material is deposited on the surface of the substrate in layers of thin films. These layers can be either structural or an oxide-based scaffolding known as a sacrificial layer. The scaffolding is then etched away, leaving only the structural layers. Surface micromachining can create very complex structures with overhangs. It can be used to create sliding structures, actuators, and free-moving mechanical gears. Even microscopic motors have been achieved using enhanced variants of the process. In order to form more complex and larger MEMS structures, micromachined silicon wafers can be bonded to other materials in a process known as fusion bonding. It's a technique that allows the seamless integration of multiple layers via atomic bonding between them. Fusion bonding allows for the use of more exotic materials such as metals, glass, ceramics, and even organics such as polymers, enzymes, antibodies, and DNA. High-aspect micromachining differs dramatically from the other two techniques in that it's reminiscent of traditional casting. Typically, a metal base is first coated with a thick acrylic layer. Then, through a mask, X-rays are projected onto the surface, creating a shaped cavity. Electroplating is then done to fill the cavity with metal, and finally the acrylic is etched away, leaving an embossed metal structure. High-aspect micromachining is one of the most attractive technologies for replicating microstructures at a high performance-to-cost ratio. Some common products micromachined with this technique include fluidic structures such as nozzle plates for inkjet printing and microchannel plates for disposable microtiter plates that are used in medical diagnostic applications. Let's take a look at those popular applications of MEMS devices we mentioned earlier and explore how they function. The accelerometers used in automotive airbag sensors were one of the first commercial devices using MEMS technology. They measure the rapid deceleration of a vehicle upon hitting an object by sensing a change in voltage. Based on the rate of this voltage change, the on-die circuitry subsequently sends a signal to trigger the airbag's explosive charge. The accelerometer mechanism is composed of a capacitive finger structure consisting of a pendulum assembly that forms the proof mass. This compliant structure deflects under acceleration or deceleration. This deflection creates a differential capacitance. The resulting voltage signal created by this is then processed by the circuitry on the device. Initially, airbag technology used a conventional mechanical ball and tube type device, which was relatively complex. Virtually every vehicle made within the last
So the video is going to go on for another 5 or 6 minutes. You have the link. I suggest that you check it. We're going to cover that material in this course in more detail, and you will see some of the statements are subjective, but hopefully by the end of the first 3 weeks you will actually have a good grasp of how this whole process has come together. Now, if you look at the milestones and what happened throughout the history of these microelectronic processes, this is a basic milestone. So in the 1939 we invented the p-n junction semiconductors at Bell Labs. These were the first semiconductor diodes. Soon after that, in 6-7 years later, they made BJTs and bipolar junction transistors in Bell Labs. And then again, once people had one junction, they figured out how to use 2 of them to make a transistor, and then once they made a transistor, they tried to figure out how to put multiple transistors on the same chip and fabricate multiple of them at the same time. This was done again within a decade. Going forward, we figured out how to make field effect transistors instead of BJTs, and then the big advantage of a FET over a BJT is the capability for miniaturization. We make FETs smaller, easier than BJTs. So once we figured that part out, how to make MOSFETs reliably, and then how to make complementary MOSFETs, both P-type and N-type, the industry took off. So in the 80s and 90s, we basically made all sorts of microelectronic components, from analog to digital chips, using these technologies, using these CMOS technologies. And in the 90s, we started to use similar manufacturing methods for micromechanical devices. Moving on, in 2000s, 10 years later, we had plenty of applications for MEMS. They were basically spreading everywhere. We had done the fundamental studies on what is possible and what is questionable with MEMS during the 1990s and the early 2000s. And then by the end of that first decade in 2000s, by 2010, the MEMS industry was well established, and it was just new applications that were coming about. So if you want to look at the MEMS specific milestones, in the 50s, people noticed some interesting mechanical properties of silicon and germanium, starting with the piezoresistive properties. They noticed that the resistance of these materials, these semiconductors, changes in response to a mechanical input. So that should ring a bell, and that should basically basically light up with a light bulb above your head, that maybe I can use this for sensing applications. In the 60s, the basic processes for microelectronic industry was developed. We used the same thing for micromechanical devices. Actually, the first MEMS device was fabricated in the 60s. In the 70s, they figured that, okay, so we need to go deeper than what you normally do for microelectronic devices. You need to etch trenches that may be hundreds of microns deep, while in microelectronics, everything is happening within the first couple of microns of the substrate. So they started to develop MEMS-specific processes like bulk micromachining. And then in the 80s, they went beyond the limitations that were imposed onto them by using microelectronics materials. In microelectronics, we use essentially silicon and aluminum only, right? And maybe a little bit of a dielectric here and there to isolate the different stuff from each other. In MEMS, we needed more, right? So they looked at surface micromachining, depositing whatever material that you need on the surface and removing the portions that you didn't want as an alternative technology. New demands and then therefore new solutions. And then 90s, people put these together, started to make devices. Tons of interesting devices came about in the early 90s. You know, you had the accelerometers that were deployed in large numbers in cars for airbag deployment and so on. And then in 2000s, as we said, things were mature, right? So now you had MEMS foundries that could provide the service to startups that could not afford their own MEMS fab and make the devices for them. And since the 2010 or late 2000s, there's just an explosion of applications. And as we said before, wearables and IoT are two of the latest examples. In terms of application timeline, you know, again, we matured. So in the early days, we were only detecting phenomena. And later on, we started to do a proper measurement. So in the early days, you were detecting a crash. Now we're doing a proper measurement of the acceleration or g-forces. And the trend is to figure out context. So not only we are measuring these quantities with more accuracy nowadays, we also want to know what caused them. You know, what happened that we had such and such change in the sensor output. We are looking for the cause of the changes, not only the changes. And that's the signal processing part. In terms of, you know, applications, you know, you can see sensors in a car. We have all sorts of sensors, and this is a traditional car. This is not one of those, self-driving cars yet. But you need sensors everywhere. You know, beyond the airbag, you need sensors in the engine, you need sensors in the brake system, you need sensors in the cabin, right, for HVAC, for example, right? And so on and so forth. And designing sensors for cars is tricky, it's difficult, it is regulated, but it is often, if you can do it right, it is very lucrative as well, right? So you have a huge market, there's a lot of customers, there's a ton of cars that are being made every year. And if your sensor is suitable for those kinds of applications and it can meet the requirements regarding, the operating environment, the price, the safety, then it's actually a very active area of usage for MEMS devices. It's a harsh operating environment in most cases. You know, you have all sorts of chemicals, you have electric shock, you have temperature variations that are much higher than what you normally expect in some other consumer applications. But it makes it also a very interesting field to work for, you know, engineers, mechatronics engineers included. In cell phones, we have tons of sensors nowadays. You have your accelerometer and gyroscope, but you also have cameras, and then your new cameras have lenses that move back and forth. These are usually microactuators that are helping you focus on different objects. The sensor itself is a CMOS image sensor. You can consider it as an optoelectronic device, an optical sensor. You have all sorts of RF MEMS components in your sensor, in your cell phones nowadays. You have a fingerprint reader in some cases, and you have a face detection mechanism in other cases. Both of them are using MEMS technologies. In wearables, you have at the very minimum a temperature sensor and maybe an accelerometer. But nowadays you have all sorts of other sensors in there as well. You have pressure sensors, and you have sensors that measure your biological signals. You have heart rate and oxygen saturation and those kinds of signals measured by your wearable devices. Now, we said that the MEMS manufacturing is different from your traditional manufacturing. Now, this is a general overview of the process, and we come back to this sequence over and over in this course. But what happens in general is that you start with a wafer, and this wafer, it's actually round in most cases. It's a circular wafer, and that's your fundamental, it's a mechanical backing, right? So this is where you make everything on it or from it. The wafer is usually from silicon. You deposit or grow the films that you need for that certain functionality. You may want to change the electrical properties of the film through a doping step. So whatever you have, you may want to make it more resistive or less resistive. Or you can actually make junctions that way. You define which areas of this film you want to keep and which areas you want to remove through a lithography process. It's a photolithography process. And then finally you remove whatever that you don't need. It's an etching process. And then this sequence is repeated. So in a MEMS process, you may go through this cycle of film deposition, lithography, and etching maybe 10 times, 5 times, depending on the application. In microelectronics, it could be tens of times or maybe even more. One other thing that is specific to MEMS applications is bonding. So in a MEMS process, at the end of the story, you have a micromechanical device that is really fragile, and you want to protect it from the environment. You're protected from all those things that can happen to it, including the drop of a particle on it that can make it dysfunctional. So bonding is a process where you attach a cap to the chip that contains your device and protect it from what is going on in the environment. Now, in this slide, again, we have a process about a video about how sensors are made. I encourage you to watch that video through the link that is provided here. And I'm going to move on to the next section to save a little bit of time. But what I ask you to do is to maybe stop this lecture video, have a look at that link, and then come back and continue the video. At the end of that story, you should see that the key to the success of MEMS and also microelectronics is batch fabrication. You're making hundreds and thousands of these devices in parallel. And then I have a few other videos throughout this lecture that I would again encourage you to go and check. The links to these videos are provided on the slides. You can basically have a look at them on your own. And in order to save the lecture time, I'm going to skip those in our videos, on our lecture videos. And then if you do it on your own, you're basically going to have better quality of sound anyway. So I'm going to stop this lecture video right now. The next topic I'm going to talk about is a MEMS design example. So I'll tell you, from the idea of doing something on all the way to actually realizing it and fabricating it, what are the steps that are required, how do we do it in software, and then eventually what do we get in return in physical world.